Please take a minute and look at your mastering scores at this point. Some people have more than 100% right now. Okay, so some people have like 105% because they've done all the assignments and they've done those adaptive follow-ups. The adaptive follow-ups are like extra credit. You don't have to do those, but it does give you the option. So if you don't have at least an 80%, remember an 80% becomes a 100%. So if you're going for minimum, then make sure that you have an overall average of 80% at the end of the semester, and I will turn that grade into a 100, okay? But if you get more than 100, I'm going to let you keep that 100 or 105 or 110, so it can actually end up adding even more points to your overall score. So if that is anything of a premise to kind of push you to continue doing them, then that's one thing that I'll do. Usually I max you out at 100. 100 is the highest score you can get in mastering, but you know, this is it for me. So I will let it roll. So if you have more than 100% at the end of the semester, I'm going to let it go. But I will tell you, there are some of you out there that have like a 10. Okay. So at 10%, that's 21% of your grade. So that means that you are losing 19 points off of your final grade right now because you haven't done any of the mastering assignments. Go back and look at them. Just make sure that if you start doing them right now and you do them for the rest of the semester, we still have 6 chapters. So if you start doing them today and you keep up with them and you do the ones that are due on Sunday nights and you make sure you get the pre-lecture ones done before you come in when we start a new chapter, if you started now, you could bring that score up to at least in the 70s, which then becomes like a 95 because 70 out of 80 is like 7/8, and so that's pretty close to being like a 90%. So that would really improve your grade a lot. So do make sure that you take a look at your mastering scores. If you do not have an overall average of 80%, start putting sticky notes around your house, start setting alarms on your phone, start trying to like remind yourself somehow to remember to do them. Because 21%, that's more than an exam grade. And some of you have like a 7% as a grade. So that's a pretty low exam grade, okay? So just saying, all right? So chapter 7, I said it's really about how molecules interact. The whole first section is kind of, again, set up into these sections. The first part is all about gases. The middle part is how liquids interact and why some molecules exist as a gas at room temperature or as a liquid at room temperature. It all has to do with how these molecules like are attracted to one another. And then the end part is really talking about another aspect of lipids, talking about membranes, steroids, cholesterols, how we'll finish it up. So gases. So remember that gases are really different from solids and liquids because gases, the molecules do not touch each other. So they came up with what's called kinetic molecular theory. This is really just like a way of describing characteristics of gases. So you don't use kinetic molecular theory with solids and liquids. You really only talk about gases this way. So one thing, particles don't touch each other. Okay, so the gas molecules in the air in this room, these particles are so far apart and they're so small that they like pass past each other, but almost never bounce off of each other. So that means that this little gas particle right here behaves as if it's the only gas particle in the room. So it's not affected by other gas particles. So there is no attractive force. So it doesn't matter if they pass really close or if they're very far apart, they behave as if there's no other particles around. They are very far apart from each other. Most gas space is just empty space. So like in the air in the room, there are these particles here, there, and around, but most of it is just empty space. Gas particles constantly move. So they don't just sit here. They're just constantly sort of floating, right? And if you've ever seen like fog, especially like in these early mornings, you see fog. If you get a chance to sort of sit and look at it, because fog is just water vapor that is so dense you can actually see it. But if you watch it, you can see that it's got this kind of like flow, almost like water. So these molecules are constantly floating about in this constant random motion. And their motion is very much determined by their temperature. So remember in the first chapter, I said temperature is really a measure of the vibration that molecules have. If you take a molecule and you heat it, it starts to vibrate faster The faster it vibrates, if you're a gas molecule, the faster you move. So their motion is completely dependent on that vibration. So temperature is all due to the vibrational activity. And as we increase temperature, we're going to increase the vibrations that gas molecules have, and that's going to increase the amount of movement that they have. In the summertime, like when it's hot, like if you look at like the roof of your car, sometimes you can almost see like the air right above, because it's so hot, it kind of gets like this kind of wavy look to it. And that is because those gas molecules right above that metal are being heated because of the sun bouncing off and heating that metal is heating the gas right above it. So it almost gets like a weird little shimmer. Sometimes you can see that on like asphalt, like in the middle of the summer, you get like this kind of weird shimmering. That is all because those gas molecules are being heated. And so they're moving so quickly that you can actually see that it causes a disturbance in the air right around those hot surfaces. Okay, so these are like points of kinetic molecular theory. When we talk about gases, there's a couple of measurements that we can do with gases that we really don't talk about with solids and liquids. So with gases, we can talk about what's called pressure. So 2 units that you're going to see with pressure, anytime you see ATM, that stands for atmospheres. Anytime you see mmHg, mmHg stands for millimeters of mercury. So remember, Hg is the formula for mercury. You've probably seen mmHg when talking about like blood pressure, which is measuring pressure on the walls of blood vessels. Well, when talking about gases, pressure is the force that these gas molecules have on the walls of their container. So the molecules, I said, they're constantly moving. So gas molecules are always moving, always moving. And they're going to bounce off the walls of whatever their container is. And that's what pressure really refers to. So those 2 units you want to be able to recognize, just like you want to recognize if you see liters or milliliters, then you know that that is volume. If you see atmospheres or mmHg, millimeters of mercury, then you want to remember that that's pressure. Pounds per square inch in Pascal, we really don't use. Pounds per square inch, that is like tire pressure, right? So if you've got to like pump up your car tires, your bicycle tire, that's what it means, is it's how many pounds of pressure. But that's really an English unit because it's pounds instead of being in grams. So we really aren't going to use this very much in class or at all in class. And we're really not going to use Pascal. That's usually used more for like physics pressures. But we will use those top 2. So how did they come up with atmospheres? Well, initially they were trying to determine the amount of pressure in the atmosphere. So if you think of people that are in Rocky Mount, we are pretty much at sea level, okay? Most of eastern North Carolina. So there is very few places in eastern North Carolina that are more than 25 feet above sea level. That's how flat it is, okay? There are very few. I was actually surprised, like went and started looking like New Bern, Greenville, Rocky Mount. I was like, geez, if we had a big tsunami, it would end up coming very far inland because we are not very far above sea level. So they said, okay, well, people that are at sea level, when thinking about atmospheric pressure, and you've probably heard about high pressure, low pressures, like on the weather, when they like there's this H coming across and an L, you've seen those in the weather. Well, that's really talking about the amount of air above and how much moisture is in that air. So if you're at sea level, you can think of, you've got this column of air going into the upper reaches of the atmosphere, this column of air that is above you. And this column of air creates this pressure or force because they're gas molecules, so they still are affected by gravity. So they said that column of air is 1 atmosphere of pressure. So that's how they came up with like a standard number. 1 atmosphere of pressure is this column of air that is above you at sea level. So if you live in the mountains, the column of air is larger or smaller? Smaller. So when you're up at high altitudes, the air pressure is less. So they talk about how there's a lower pressure, your ears pop. If you go up in a plane, then it's even higher. That is why they have to pressurize a plane, because the pressure is so low that it would just collapse. So lower pressure in the mountains. So what about the people that tried to go down to the Titanic? That was wrong. It was like not the best ship that they could possibly use, right? So they had to go like 30,000 feet or something under and down to the bottom of the ocean floor. What was the pressure down there? Not only are you talking about the column of air, but now you got water on top of it too. And water weighs a whole lot more than air. It's a lot more dense. So the pressure was so intense. Though you have to have like those submarines and such, the walls and how they're reinforced to be able to withstand those pressures. Those walls are super thick. And like that little ship was not really designed to actually be able to do that. And it didn't make it. It like just kind of like got crunched like a tin can. But that's because of really high pressure. So if you go deep underwater, and if you've ever been in like the deep end of a pool and you try to go down to the bottom, you can feel that pressure. It like makes your ears kind of hurt. Just even going 10 feet underwater, these people were like 35,000 feet down. So that's what pressure kind of came out. That's how they originally came up with this. So then they said, okay, well, atmospheres, okay, one column of air above us, that's an atmosphere. But what is that? How can we measure that and have it in a metric value? So they use mercury as a way of being able to measure one atmosphere of pressure is equal to or creates a column of mercury in a little pool that would be 760 millimeters tall. So this is where the equivalents come in. So one atmosphere, 760 millimeter tall mercury column, is going to have an equivalent of one atmosphere. And we really don't do very much unit conversions. We'll use either one. Like you'll either have numbers in millimeters of mercury or you'll have numbers in atmospheres, but that's kind of where they're equal. Okay, so a lot of this research, a lot of the experiments that led to this understanding of gases really happened like 350 years ago. So this is not something like with radiation. Remember, like X-rays, those are all things that are only about 100 years old. This was something that they could study because it didn't involve really technical tools. They had to have a way of measuring pressure, of determining the amount of force on the walls of a container, and they have to be able to measure volumes and also temperature. So they had to have thermometers. So pretty simple kinds of things that they needed. So in the 1600s, Robert Boyle, he was an Irish chemist. So he looked at keeping gas temperatures the same. So he kept temperature constant. So that means that those molecules are vibrating at the same frequency, okay, same temperature. He found that if he took a sample of gas, put it into a container, and changed the pressure, that it would change the volume. So remember that these gas particles are spread out. There's a lot of empty space. That means that gases are compressible. I can take gas molecules and force them into smaller spaces, but what he found is that causes a change in pressure. So if we look at these three syringes, the first syringe, we'll say that that's the original syringe, okay? That's your like starting point. So in this, if I have this initial pressure, so I'm going to say that my pressure is 1. The pressure here is 1 atmosphere. And the volume that those gas particles take up at 1 atmosphere is shown by the little notches on the syringe. So you would say it's how many notches? 3. Kind of looks like 3. In fact, this looks like a little 3 cc syringe. So this is like a 3 milliliter. So the volume initially is 3 milliliters. And so can you see the little red? You can see the little red gas molecules moving around inside, but that's at 1 atmosphere of pressure. So then he said, okay, if I take this and I double the amount of pressure on the syringe plunger, so now my pressure is 2 atmospheres. I'm going to double it. I'm going to push down and create a 2 atmosphere pressure. What does that do to the volume? Instead of 3, the volume looks like it's kind of at about 1.5, right? So that's the middle syringe. So now my volume is only 1.5 milliliters. And so then he did the third experiment where he took those gas molecules and he tripled the pressure compared to the original. So now my pressure is 3 atmospheres and my volume is 1 milliliter. So he said, as I increase the pressure, increasing the pressure does what to my volume? Decreases. So he said, there is an inverse proportion, which means if one goes up, the other goes down. So if I increase pressure, I'm going to decrease volume. If I decrease volume, that will increase pressure. If I increase volume, I'll decrease pressure. So whichever one goes up, the other one goes down. They called it an inverse proportion because they go in opposite direction. The best example of Boyle's law as a normal application is really just the act of respirations. Just breathing, the physical act of breathing, or ventilation is what they call it, is really the best way to think about Boyle's law. And this is because, and I find it's easiest really just to draw it, inhaling and exhaling, just think about them as being 2 separate events, okay? So when you start an inhale, so like think at the end of your exhale, so you start your inhale. When you start an inhale, inhaling is actually called an active process. It is active because it involves muscle contraction. So without muscle contraction, inhaling can't happen. So that's what happens with people with polio, because they didn't have, their muscles were paralyzed and they had to be put in on a ventilator. Muscle contraction is what starts inhalation, and there's 2 groups of muscles that are involved. The first one is really the most important one, and that is the diaphragm. So your diaphragm is the muscle that separates your thoracic cavity, which is where your heart and lungs are, from your abdominal pelvic cavity, where your liver, stomach, small intestine, large intestine is. Okay? So it is this muscle that physically divides the ventral body cavity into upper and lower parts. So you can see it here. This is the diaphragm. So muscles, when they contract, do they get longer or shorter? Shorter. When muscles contract, they get shorter. So at the beginning, think of the diaphragm like a dome. But now when it contracts, it is going to get shorter. So that means that the diaphragm is going to go from being more domed to being flatter. So the diaphragm is going to go down when it contracts. So you can kind of see the little arrows. When the diaphragm contracts, it gets flatter instead of being more domed. The other set of muscles are muscles that you find between each rib. So they call them intercostals. Inter means between. Costals actually is referring to ribs. So the costal regions are your ribs. Intercostals are, so think like you've got your 12 pairs of ribs. So you've got these muscles that join the ribs above and below. These muscles, the external intercostals, what they do when they contract, they actually pull the ribs up and out. And if you put your hands on your chest and take a breath, you can feel it. So you can feel your ribs come up and out as you do an inhale. So this is going to go like this. Up and out, up and out, up and out, up and out. Okay, so that means that the thoracic cavity, the ribs are going to go this direction. So now it's more like this. So instead of being sort of more domey looking with the diaphragm kind of bent going up, That's going to drop down, ribs go up and out. So what would you say happens to the volume inside of the thoracic cavity? Does it go up or down? Up. Can you see that? So if the ribs go up and out, diaphragm goes down, the space inside of your chest goes up. So my volume increases. So what did we say with Boyle's law? If volume goes up, what does pressure do? Goes down. So now the pressure inside of the thoracic cavity goes down. That creates suction. Negative pressure is a suction action. And the only way to balance the pressure is to allow air to get pulled in. So air gets it pulled in through the trachea, which then divides into the bronchi, and then leads into each lung. So as air flows in, those lungs inflate. And it continues until the pressure balances again. So if you sort of think about breathing for a minute, you feel as you expand the ribs, you can feel that air automatically get pulled in. It is a natural response to the change in volume and pressure. Your lungs are basically just elastic balloons. Your lungs don't do anything to breathe. Your lungs are just there. The only thing they do is they stretch and fill with air to try and balance out the pressure changes due to that increase in volume. So when you inhale, volume goes up, pressure goes down, and that sucks air into the lungs. So now you're at this. You're at the top of an inhale. At the top of an inhale, now we're going to start an exhale. So exhale is called a passive process. It's passive because when you exhale, muscles relax. So this, like if you ever see somebody that snores, that inhale is really where the big snore is. It's like, and then the exhale is like, it's a much more relaxed sensation. I have a pug, so I can really make that noise because I listen to that. She like snores in my ear almost all night long. But that inhale is the active because it's expanding, increasing volume, decreasing pressure. The exhale is this passive because what happens is the diaphragm, which is now flatter, it relaxes. And so now the diaphragm is going to, as it relaxes, it gets longer. So that means that it starts to move upward. So the diaphragm rises. The external intercostals, they stop pulling the ribs up and out. So now they just automatically start dropping back in. So the ribs begin to go back in and down. And so now the volume inside of the thoracic cavity does what? Decreases. So as things come in, this comes up, the volume inside goes down. So if I decrease the volume inside of the thoracic cavity, what's that going to do to the pressure? Right? So remember we said they go in opposite directions. So if the volume goes down, the pressure goes up. That, an increase in pressure, that creates force. That creates a push. So now I have force inside of the thoracic cavity. The only way to allow that force out is to let air go out of the lungs. So again, same direction. As that volume goes down, pressure goes up, and that creates the push or the force that pushes air out of the lungs. So if you sit and breathe a bit, because you never think about breathing, you just breathe, right? 12 to 18 times a minute, you just breathe. Sometimes you breathe faster, sometimes you breathe slower, but you just breathe. Most people don't like sit and contemplate it. But if you sit and feel that flow, you can feel ribs up and out, air automatically starts flowing in. Ribs going in and down, air automatically starts going out. It's kind of hard to feel your diaphragm, but you can kind of feel your ribs going up and down as you breathe. So it's a little easier to kind of imagine that volume change that occurs with inhaling and exhaling. So this is all just Boyle's law. Change in volume, change in pressure. Increase volume, decrease pressure. Decrease pressure, increase volume. If one goes up, the other always goes down. Okay? So we can also calculate these. So if we have actual measurements of pressure and volume, we can calculate changes that occur. So what Boyle's law found, he said, these are inversely proportional. So remember I said you're going to expect if one goes up, the other goes down. So that's the inverse proportion to it. But I can calculate it using this formula. So if I know an initial pressure and volume, I can figure out or I can find the change that occurs so that I can figure out a final pressure and volume. So you can use an I or an F. I oftentimes end up using P1 and V1. So pressure of P1 and V1 would be your starting pressure and volume. If you multiply them, they will be equal to the final pressure and volume, which I oftentimes just call P2 and V2. So that's what you end up with. You will always know 3 out of the 4. So you'll be given either both pressures in one volume or both volumes in one pressure. And you'll have to rearrange this formula to be able to figure out how to solve it. So for example, if I know P1, P2, and V2, and I need to find V1, what do I have to do to be able to use this formula and find V1? Which do I have to move? I've got to move P1. I've got to, if whatever you have to find, you've got to get it all by itself on one side or the other side of the formula. So if I need to find V1, I have to move P1. So if I need to move P1, how do I move that to the other side? Divide both sides by P1. So do you see if I divide this side and this side by P1, what happens to the left side? P1 will cancel. So do you see that then P1 and P1 cancels? So all I did was just move P1 to the other side. Now I can plug in my numbers and my answer will tell me V1. So I just say P2 times V2, whatever those numbers are, divided by P1, that'll give me V1. So in all cases, you're going to get 3 out of 4 of your numbers. You will have to rearrange. Inevitably, you always end up having to rearrange the formula, but then all you got to do is plug it in. So here's sort of the steps, and we're going to walk through one. I'm going to let you do one, and we'll go on and do the next one. But with Boyle's law, you always want to figure out, what do I know? Okay, what are the 3 values? Identify which is which. So make sure that you figure out, okay, what's V1? What's P1? What's V2? What's P2? Figure out which one you don't know. That's your question mark. Then you got to rearrange the formula. That's step 2. So you want to make sure that whatever you don't know is all by itself on one side of the formula, and it can be on the right or the left. It doesn't matter. It just needs to be by itself. The third thing is then just plug in the numbers. So you put the numbers into the equation to solve it. The last thing with your answer is make sure that you check significant figures in the problem and then round. Okay, because most of the time on your calculator, you're going to get 8 or 9 digits, and so you can't keep them all. That's what you use, is you always go back to the numbers in the problem to figure out for rounding. So here's the first one. So if you read a problem, if a sample of gas changes from a volume, so I know volume of 82.3 liters to 26.5 liters, what was the initial pressure? So if you see volume and pressure values, I see volume, I see pressure. As soon as you see that, then you know that you're going to use Boyle's law. So one challenge is you first got to figure out, okay, which law do I have to use for this one? But if you read the question, pick out what units are there. Liters are volumes, at millimeters of mercury is pressure value. So I know I'm using Boyle's. So I know that I'm going to take P1 times V1 to equal P2 times V2. I know that that's the formula that I'm going to use. Now I need to identify, okay, what's P1, V1, P2, and V2? What are each of these? So just read through. If a sample of gas changes from a volume of 82.3 liters, so what is 82.3 liters? So first, what is it? It's a volume, right? Liters is volume. Is it the initial volume or the final volume? It's initial. So this is V1. And it changes to 26.5 liters. So that is V2. That is my final volume. So I know these, 26.5 liters. What was the initial pressure? It's usually the second part of the problem when it asks you what was. Now I know what's my unknown. The initial pressure. So what I don't know is this, because initial pressure, that's P1. So when you find the what was, now you know what the unknown is. If the final pressure is 1,825 millimeters of mercury, so that is what? That's got to be P2, because the final pressure. So 1825 mmHg. Okay, so identify what each of the units is. I know that for some people, they're like, that just takes too long. But if you do it this way, then you won't end up flipping your volumes, okay? Identifying the volumes incorrectly, like saying, oh, well, V2, oh, that's 82.3. Because that's usually the only reason people get these questions wrong, is that they don't break it down and they just randomly put numbers in because there's a volume, I'll put it here. Oh, there's another volume, I'll stick it there. They don't stop to pull it out. So pull the numbers out of the problem so that you can set it up. So now I've got everything identified. I know my unknown. So I've got to find P1. So in my formula, what do I have to move? So I got to get P1 by itself. What do I move? V1. So see over on the left, P1's on the left. I got to move V1. That means I have to divide both sides by V1. That will cancel V1 on the left and leave me with P1 equals P2 times V2 divided by V1. Now just go plug your numbers in. Just make sure that you use what you've identified so you don't get them flipped up. So P2 is 1825 mmHg. V2, 26.5 liters divided by 82.3 liters. That is going to be P1. Calculator, 1825 times 26.5 divided by 82.3. I got 587.63669 millimeters of mercury, not liters. mmHg. Okay, so that's like all of them, but I can't keep all of them. So then I go back to the question at the top. So based on V1, P2, and V2, how many significant figures should my answer have? 3. Okay, 82.3, 3 significant figures. 26.5, 3 significant figures. 1825 is 4, but remember, it's always the smallest number of significant figures in the problem. Those are all measured numbers, so I would use those. So then, from the left, the first 3 significant figures I get to, the 5, the 8, and the 7. Those are the first 3 significant figures. The next number is a 6, so what is that going to do? Round it up. So this would be 588 millimeters of mercury. Okay? So now I want you to do this one. All right, so when you look at this, you see pressure and volume. So that tells you to use Boyle's law. So just look through the problem to look for what are my units. I see pressure of atmospheres, volume in liters. That's how I know to use Boyle's law. P1 V1 equals P2 V2. I know P1 because it says it changes from 2.5 atmospheres, that's P1, to 6.4 atmospheres, that's P2. What will be the final volume? That's my question mark. So V2 is the one that I do not know if the initial volume was 0.025 liters. So I know V1, I don't know V2. So I've got to move P2 from the right side of the equation, so I have to divide both sides by P2. So notice that that allows P2 to cancel on the right, and it leaves V2 all by itself. Then just plug them in. So P1 is 2.5 atmospheres, V1 is 0.025 liters, divided by 6.4 atmospheres. Atmospheres will cancel in that math, leaving you with just liters as your answer. And I got 0.009765625 liters. Did anybody not get that? Okay, so when you put in your calculator, I got a whole bunch, but I can't keep them all. So how many significant figures do I need to round this? 2, because 2.5 atmospheres, 6.4 atmospheres, 2 significant figures in each. 0.025 liters, that's still just 2 significant figures. So coming from the left, remember that those zeros stay, but they are only telling you where the decimal is. So they stay. The first 2 significant figures you get to are the 9 and the 7. The next number is a 6. So what does it do? Rounds up. So I keep the zeros, and that 7 becomes an 8. There's 2 significant figures in that answer. That would be the correct volume. Okay, so if you get a problem, look at the units, determine if it's Boyle's law. If it's Boyle's law, you're going to use that formula. You're always going to have to move one of the units to the opposite side. Second gas law, and really the only other one we're going to talk about, Gay-Lussac's doesn't really get very much cred, but it's a good gas law, but we're just going to cover these 2. So the second one is Charles's law. So French, same about time, mid-late 1600s was when he was looking at this. And so he said, okay, if I can keep the pressure the same, so I have to have some kind of chamber that if the pressure can stay the same, if I change volume, temperature is affected by a gas as well. So volume and temperature have a relationship. He found that if you increase the temperature, what do we say temperature is? It's really a measurement of that vibrational activity, right? So if I take a gas and I begin to heat it, will those molecules vibrate more or less? If I take a gas and I begin to heat it, will the molecules vibrate more or less? More, right? So, and if they vibrate more, they are going to need more room because they're going to be moving faster. So if I increase temperature, that is going to do what to volume? If they vibrate more, they need more room, volume goes up. So he found that these are directly proportional. If one goes up, the other goes up. If one goes down, the other goes down. So if I increase temperature, that will increase volume. If I have to keep pressure the same, I have to allow gases to be able to expand when I heat them. Think of like the hot air balloons, right? So they just like turn on the little burners and begin to heat that air and it just begins to fill the balloon. As I increase temperature, that increases that volume. Same thing happens though if I have a sample of gas and I decrease the volume, the temperature is going to have to decrease as well. If I want to keep the pressure the same, if one goes up, the other goes up. If one goes down, the other goes down. And my best example for this is something that became like this weird tradition in our family. So when so my oldest child is 34, my youngest child is 31, older than most all of you, okay? But when they were kids, we started this when they were like 4. So at 4, you got 3 regular balloons and 1 Mylar balloon. That was your age, okay? Then 5, then 6, then 7. So then when they get into their teens, they're still like, we still get all the balloons, right? And I was like, Well, you're like 16 years old. Aren't you too old for this? No. We want the balloons, mama. So, all right, fine. But I will tell you, my oldest child, she was born in the end of August. So what is the end of August like in Eastern North Carolina? Hot as blazes, okay? So end of August, it's her 16th birthday. So I got to go get 15 balloons and 1 Mylar balloon and like completely fill the kitchen. Where do you go if you have to get that many balloons? I don't go to Harris Teeter. I don't have that much money. I get paid teacher salary. We go to Dollar Tree. Yes. So we go to the Dollar Tree. I lived in Wilson at the time. So the Dollar Tree over by the movie theater. If you've ever been to the Carmike, there's like, it was a Dollar Tree. Yeah, I know it's really sketchy now, but there's, and I don't even know if it's still there, but that's the one where we always went to. So it's like this black asphalt parking lot. So drive the mom van, because I drove a mom van until my kids went to college. Yes, I did. Drove the mom van, get there, park in the parking lot, go into the store. Okay, so then you're getting the Dollar Tree lady. You're like, can I get like 15 balloons? And she's like, gives you the face. What is wrong with you, lady? Okay, all right. So then you're like, yeah, 15 balloons and then 1 fancy Mylar one, because I can't buy all the Mylar ones, just regular ones. And so I'm going around like, okay, we're gonna need some plates. We're gonna need, so you always end up like getting more stuff, right? So in that time, there's a good 20 minutes that my car has been sitting out in the parking lot. The temperature inside of my car is doing what? Increasing, okay? So now it's not 70 degrees inside of my car like it was when I was blowing the air conditioning as hard as I could all the way there. Now it's like in the 90s inside of my car. But I've just gotten all these balloons. So I have 16 balloons walking out of the Dollar Tree trying not to like drop everything. Going from a 70-degree store, the air inside of those balloons is 70 degrees. Go and put these balloons into a 95-degree car now. What did we say starts to happen? So if you increase temperature, as those gas molecules go from 70 and start to warm in the hot car, what happens to the volume? It begins to expand. Well, I just got these balloons. So they're pretty much as expanded as they can get. So they're nice and tight. So jump in my car, driving back home, and what inevitably would happen? Bang! And you're like, what was that? The first time that happened, I was like, someone's shooting at us. It scared the tar out of me. Okay. After that, it was almost inevitable that the older one would come in and be like, 1, 2, 3, 4, 5. Like legit, she is one of those kids. Okay. I'm going to like count every single one. And there'd be like one popped balloon hanging down. She'd be like, I don't have all the balloons. Yeah, she'd be traumatized. She was a very dramatic child. She still is, but it's just fine. But that was always, and that's like my best example of Charles's law, okay? Because if you take a balloon at 70 degrees and you heat it to 95 degrees, those gas molecules are going to start moving faster. And if they move faster, volume is going to go up. And there is a limited expansion that balloons can actually do. So I inevitably ended up losing a balloon or two. Yes, I know it was like, I was really glad when I finally went to college. I was like, no more balloons. She was like, you should send balloons to my dorm room. I was like, really? Really, child? Okay. So we're going to use a little different, the formula is different in doing this calculation. One other thing though, Charles's law had a challenge because he said, this works great. If volume goes up, temperature goes up, volume goes up. If temperature goes down, if I get to 0 degrees Celsius and I keep decreasing the temperature, what happens to my numbers? They get all out of whack. They're not going to keep, my 0 Celsius below 0 is now a negative number. And the number starts increasing instead of decreasing. So it doesn't fit using this if I'm looking at anything below 0 degrees Celsius. So he said, we have to calculate a 0 degree that is absolute 0. So remember, I said temperature is really a measurement of the vibrational activity of molecules. So they had to calculate how cold would something be, what would be the temperature at the point that molecules stop vibrating. So if they don't vibrate, they can't not vibrate anymore. So not vibrating would be the coldest possible temperature, and they called that absolute 0. So it got a name that is called Kelvin. So you cannot use Celsius when doing gas laws. You need to use absolute zero. This is the Kelvin scale. Now, Kelvin scale is the exact same scale as Celsius. So you don't have to do like weird like math to try and go from Celsius to Kelvin, Kelvin to Celsius. The difference is the 0 degree point. At 0 degrees Celsius, that is 273 degrees Kelvin. And you're really not supposed to put a degree sign, but if you have 0 Kelvin, that looks like okay. So that's kind of strange looking. So that's why I still put a degree point. Okay? 273 degrees Kelvin is 0 degrees Celsius. So that means that my 0 degree Kelvin is negative 273 degrees Celsius. So I'd have to chill my sample 273 degrees below zero, below the freezing point of water. In Fahrenheit, this is minus 459 degrees Fahrenheit. Almost 500 degrees below zero on the Fahrenheit scale. And we're not going to use the Fahrenheit scale, but most people they think about the Fahrenheit scale, so that's a little more relatable. So that's really, really cold. And in fact, scientists, because of course they had to, scientists have made freezers that get within a few degrees of minus 459. That cold. Okay? So think of that. That's where these molecules, they just stop vibrating. So that's actual zero. So it's pretty easy to go from Celsius to Kelvin and Kelvin to Celsius. To go from Celsius to Kelvin, you just add 273. To go from Kelvin back to Celsius, you just subtract. Because the actual every degree is equal. So a Celsius degree and a Kelvin degree are the same size. So it's just a matter of making sure you add or subtract 273. So if you're given, and most of the time when you get a problem with Charles, if I know something in Celsius and I want to know what it is in Kelvin, just add 273. So Celsius to Kelvin, you just add, because that's taking that absolute zero into account. So temperatures will never be a negative number. If I've got a Kelvin answer and I got to go back to Celsius, you just subtract 273. So you don't have to do anything else except just that. Just add or subtract. So if I know a Kelvin value and I want to convert it to Celsius, you just subtract 273. Same size degree increments. It's just where the 0 point is. Kelvin's way down at absolute zero. But you're going to solve these basically the same way. You're just got to remember to use the right formula. And one of the tricks is you've got to read the problem. If you see liters, milliliters, if you see volume, and you see degrees Celsius or Kelvin, temperature, then you know you've got to use Charles's law. Okay, so Charles's law keeps pressure constant. So if there's no atmospheres, no millimeters of mercury in the problem, then you know you've got to use Charles's law to solve it. And this is what you do to solve it. Okay, same thing. Go through the problem, identify what is V1, T1, V2, T2. Which one don't I know? Rearrange the formula so that I can get the answer, plug in the numbers, then at the end, check significant figures, okay? So you're just still gonna do the same 4 steps. So we'll walk through this one, and then I'll let you do one to practice. So a sample of gas has a final volume of 24 liters at 105 degrees Celsius. So when you see liters in Celsius, you know that's gonna be Charles's law, because that's volume and temperature. So I know that I'm going to use this. So that's going to be my formula. V1 over T1 is going to be equal to, in a direct proportion, of V2 over T2. So a sample of gas has a final volume of 24 liters. So 24 liters is what? Is it V1, T1, V2, or T2? T2. V2, sorry, V2, because it's a final volume, so that's V2. Final volume is the second one. At 105 degrees Celsius, so that is, those are grouped together, so that's T2. So 105 degrees Celsius. What was the initial volume? So that is my what was. So which one don't I know? I don't know V1, so that's my question mark. If the initial temperature was 25 degrees Celsius, so that is T1. Okay, so I've got them. So this is the first one, is I'm identifying what are the three things I know, which one don't I know. Before you go any further, put yourself a little asterisk. With Charles's law, you need to convert all of your temperatures to Kelvin. So 25 degrees Celsius, how do I get Kelvin? What do I got to do? If I'm going from Celsius to Kelvin, I have to add 273. If your temperature becomes a negative number, you did it wrong. Okay? So if you subtracted 273, you'd end up with a negative temperature. You cannot have a negative temperature in Kelvin because Kelvin 0 is at the very bottom. Okay? So 25 plus 273 is 298. So 298 degrees Kelvin. 105 degrees Celsius, add 273. That's going to be 378 degrees Kelvin. So now I've got my temperature values in Kelvin. So as soon as you do your identification, go ahead and make sure that your temperatures are in Kelvin. So now I got to solve for V1. So looking at the formula, V1 is on the left. So I'm going to have to move T1. How do I move T1? I got to multiply both sides. Okay? So do you see that T1 is in the denominator? I've got to move it to the other side. The only way to get it to cancel is I need to multiply both sides. And this way, T1 and T1 will cancel. Now remember, that means now V2 is going to be multiplied times T1. And then divide by T2 for your answer. So V2 is 24 liters times T1, which is 298 Kelvin, and then divided by 378 Kelvin. I got 18.92063492 liters. Can't keep them all. Got to figure out how many significant figures in my answer. 2. 24 liters, 2 significant figures. 25 degrees Celsius, 2 significant figures. So 2. So the first 2 significant figures in that answer, the 1 and the 8. Right? So from the left, the first 2 significant figures is the 1 and 8. Next number is a 9. So what's that going to do? Round it up to 19. So I'd have 19 liters. Okay? Go back. Don't use like your Kelvin numbers. Always go back to the measured numbers in the problem. Okay? All right. So one for you to do. A balloon one. All right. All right, so in this, you see volume and temperature, so you know you're going to use Charles's law. Going through and identifying V1 is 12.5 liters, T1 15.5 degrees Celsius, T2 89.5 degrees Celsius. Before you go any further, make sure you convert your temperatures to Kelvin. Just add 273. So I added 273 to T1 and T2. Then I got to rearrange the formula. I got to know V2. V2 is the question that I don't know, that final volume. So to get V2 all by itself, I have to multiply both sides times T2. So that's going to cancel it on the right, moving T2 over to the opposite side. One thing to remember, if you've got to move something, if it's in the numerator, it always goes in the denominator on the other side. If it's in the denominator, like T2 is, it'll always end up in the numerator on the other side. Just when you're doing rearranging of formulas, just make sure that you always set it that way. Then I just plug them in. So 362.5 degrees Kelvin, that's T2, times 12.5 liters, that's V1, divided by T1, which is 288.5 degrees Kelvin. I got 15.7062391 liters. Anybody not get that? All right, and then go back up, rounding. How many significant figures in my answer? 3. So 12.53, 15.53, 89.5, they all have 3 significant figures. The first 3 significant figures, the 1, the 5, and the 7. So the next is a 0, so what happens? It all just gets dropped off, right? Anything less than 5 gets dropped off, so this just ends up being 15.7 liters. Okay, there is a dynamic study module due Sunday night on gas laws. Okay, and so they do some just sort of like thinking about like what happens with volume and temperature changes, what happens with pressure and volume changes. So some of them are more like what happens to the balloon if the volume goes up, that kind of stuff. But then there are some where it's actually getting you to do some of the math. So just follow through, do the same steps each time. I know that it might seem redundant, but I will tell you that the only reason people get these wrong is because they don't write them out. Because they look at the problem and go, oh, I know this, and they end up flipping volumes. Or they don't do their Kelvin conversion. Like, those are really the only reasons. And it's like, all right. So there's a couple. We are not going to talk about Gay-Lussac. Gay-Lussac, interesting guy. Okay. Another Frenchman, but he studied pressure and temperature. So there is a pressure-volume relationship, volume and temperature relationship, pressure and temperature. So pressure, volume, temperature all end up having an effect in sort of like the characteristics that gases, known samples of gases, have. There's an extra one. We'll do this one next time. Well, not that one, because this one I think is a pressure temperature one, so we won't do that one. But there's one here. This one is volume and temperature. So we'll do this one next time, just another one to practice. So if you've got your PowerPoint, you can practice that one. So we've got a couple minutes. So the relationship between gases, remember, so I said, so gases, think about them as being like this, right? Very spread apart, rarely come in contact with each other. Most gases, it's all empty space with just little molecules here, there, scattered. That is why you can take gases and you can compress them, because there's so much empty space. You can push them into very tight areas. You can't really do that with liquids and solids, right? Because solids, remember when we talked about these, we said solids are extremely close together, very tightly packed, in a very regular arrangement. I can't take those and squeeze them any tighter. You can't take the desk and compress it into any smaller space, because there is no space between molecules. Liquids, more like solids, because liquids have just a tiny bit of space so that molecules can flow past each other. So remember that in this, they are still touching each other, but there is enough space that allows them to flow. So you can pour liquids, you can't pour solids, and you really can't do much with gases except compress them. Okay? So most of the time, if you take a solid and you convert it to a liquid, you melt it. Okay? And you have to add energy, because remember, those are vibrations. Okay? Solids have the lowest kinetic energy. They're the closest together, the least amount of vibration between molecules. Liquids start to vibrate more, which is why they need to be able to flow. And then if you add a lot of energy, you can take and boil a liquid and convert it into a gas, right? And then, so that, like, to make that happen, it's very slow if you just set water out. But if you add a lot of heat to it, you can make it change and boil faster. You can also do the opposite. You can take gases, convert them to liquids, condensing. You can also take liquids, throw them in the freezer, pull more of that energy out, and they'll get into a more regular arrangement back into a solid. So those, you're much more sort of familiar with, gases to liquids to solids. There actually is another side to this triangle. It doesn't happen very often, and it doesn't happen very fast. Some molecules will do it more than others, but I don't know if you remember, did your grandmother have ice cube trays in her freezer? Okay, so I did. This is the first freezer that I've ever owned that has an automatic ice maker in it. Okay, so like my kids' friends would come over and they were like, oh, look, they have ice cube trays. My grandma has ice cube trays. Like, that was always like a comment that they had. And they were like, but do you remember way back, or remember in your grandma's, did you ever pull an ice cube tray out and like the ice cube tray was like, the ice cube was tiny? You were like, why didn't you put any water in here? Okay, they did. But ice in the freezer, because it's so dry, that solid ice will actually go through what's called sublimation, where the ice actually goes directly into a gas phase. And that's why, so for us, it usually happened like if we were gone for a couple of weeks. Well, it really started happening when they weren't home all that much, because then we didn't use the ice. They were notorious for leaving the one ice cube in the tray. They used to make me crazy. The cubolo. Who left the cubolo? But this does happen. Ice cubes can sublimate, so that cube will actually get smaller and smaller and smaller if you don't actually use it, because it's in that really dry freezer. And so that dryness will actually allow it to go from a solid directly into the gas phase. If you've ever played with dry ice, that is a solid carbon dioxide. So they take carbon dioxide and they chill it to the point that it actually freezes into an ice, but it never melts. It actually just sublimates. So as soon as it warms enough, that carbon dioxide goes directly back into being a gas, and that's why it just disappears. Like, it never melts. There's never any liquid. It doesn't go through that stage. So those are just some of the differences. Liquids and solids, because they're so close together, they have a much stronger interaction with other molecules. And this is where it gets to what we call intermolecular forces. Gases really don't have this. Liquids and solids have this intermolecular forces because the molecules get so close together. So next time what we're going to talk about is we're going to talk about these 5 intermolecular forces, London forces. The 2 in the middle are polarity, like polar molecules have dipole, dipole, and hydrogen bonding. And then the last 2 we're going to talk about is what you see with ionic compounds, so salts. Salts when they interact with water, and then just salts all by themselves. So we'll talk about these ones. This is kind of the middle section of this chapter, and then we should be able to finish up this chapter next time. Okay, so over the weekend, go ahead and start working on, get that gas law dynamic study module down. You can start working on the post-lecture assignment, especially any of the gas law questions for chapter 7. I have